Welcome back to the deep dive. Our job is to take these incredibly dense technical topics, pull them apart, and give you the insights that matter.
And today we are really getting into the weeds.
We're focusing on the software that truly runs the modern world. Electronic design automation, EDA.
This is the software used to design and verify literally every modern computer chip.
And this whole field, it operates right at the absolute edge of what's computationally possible.
Oh, absolutely. We're talking about tools with massive memory needs, hundreds of gigabytes of RAM is common, and the runtime, how long a job takes to run, is often the main competitive difference between two companies.
Speed is money.
Speed is everything.
And because of that, the entire industry is built on a foundation of C++, decades of it. Which brings us to this great friction point our sources call the safety performance paradox.
Right. You need that raw, zero-cost performance for speed, but you also need absolute guaranteed stability.
Because if your design tool crashes, say, 48 hours into a 3-day simulation,
It's a catastrophe. It's an enormous expense, a huge setback. And C++A, well, it really struggles with the stability side of that. It's just so prone to memory errors, use after free, data races, all the classics.
and this is where Rust enters the picture. It promises to eliminate that entire class of bugs at compile time, giving you the safety without giving up the speed.
That's the promise.
So our mission today is to go beyond that promise and get into the engineering reality, because this transition it's not simple. We're going to break down the 4 biggest friction points for adopting Rust and EDA, and then look at the really ingenious solutions teams are using to make it work.
Let's do it.
Okay, so let's start at the very heart of the problem. Algorithmic friction. The core data in EDA. We're talking net lists, placement data. It's all these huge interconnected graph structures.
And these graphs have 3 traits that are, well, fundamentally in conflict with Rust's philosophy. They have high mutability, tons of sharing, and critically cyclical references.
And Rust's core safety rule, the ownership model, just collides with that head on.
It does. The rule is simple. You can have one mutable reference to data, or you can have many immutable references, but you can never, ever have both at the same time.
So if you're writing an algorithm that needs to, move things around on a chip design, you're constantly needing to read one part of the graph while writing to another. What happens then?
You hit a wall. It's what developers call the contagious borrow problem.
Okay, unpack that for us.
So let's say you need to modify one tiny cell, a child node in this giant graph. You take a mutable reference to it. The borrow checker, to be safe, doesn't just lock that one cell. It can effectively lock the entire parent structure.
The whole net list.
Often, yes. Which means your algorithm, which needs to jump around and make other changes, it's frozen. Your necessary graph manipulation completely grinds to a halt.
So this isn't a bug in Rust. It's a mismatch in paradigms.
Exactly. C++ lets you do this with raw pointers, but that's precisely why it's unsafe. To get Rust safety, you have to fundamentally rethink how you structure your data.
Okay, so if raw pointers are out, what's the high-performance solution? This is where we get to that first big aha moment in the research. The indexed arena pattern.
This is the key. It's the pattern that makes Rust viable for these complex graphs. The idea is, instead of creating objects and linking them with pointers, you put all your objects, your cells, your wires, into one big centralized memory pool, the arena.
And you don't use pointers to find them.
No, you use simple integer handles, or IDs. They're just small numbers, basically an index into the arena's storage.
And because an integer is just a value, not a memory reference.
Since the borrow checker doesn't care about it, you can copy it, share it, pass it around as much as you want. There are no lifetime rules to violate.
Which immediately solves the cyclical reference problem.
Gone. Instead of 2 pointers pointing at each other, you just have 2 objects that each hold an integer ID. The ownership of the actual data is managed entirely by the arena itself.
You get performance that's very close to C++ Mary, but with all of Rust's safety guarantees for almost all of your code.
That's the win. But there is a trade-off. It's a cognitive one. Your code is now working with a level of indirection. You're always asking the arena for the data associated with a handle, which can feel a bit unnatural for developers coming from a C++ world of direct pointer access.
Right. So moving on from the data structures, the next big hurdle isn't abstract, it's industrial reality. Let's talk about the interoperability crisis.
EFFI crisis, yeah. The foreign function interface. The reality is that the entire EDA world is built on decades of C++ code. Rust has to talk to it.
But it can't just link against a C++ library directly.
Not reliably, no. C++ doesn't have a stable application binary interface, an ABI. Different compilers can lay out objects in memory differently. It's a mess.
So what's the bridge?
The only reliable bridge is the old stable C ABI, and this has massive cost implications.
Let me see if I get this. It means for every single C++ function or data structure Rust needs to touch, your team has to go and manually write and maintain a separate wrapper function using extern C.
That's it. It's this brittle, manually maintained translation layer. And that is pure costly friction. It adds zero new features. You're paying for the new Rust code, you're paying to maintain the old C++ code, and you're paying to maintain this fragile bridge between them.
And it gets even worse with more advanced C++ features, right? I'm thinking about templates.
Templates are a nightmare, an absolute nightmare for FFI. Rust has no concept of a C++ template. So if your legacy code has, say, a myFunctionT, you have to manually instantiate and export every single version Rust might need.
So my function gets one C name, my function double gets another.
And my function custom struct gets a third. You throw to do for every single one. It just doesn't scale. For a 10 million line EDA tool, it's an administrative catastrophe.
And here's the real kicker, the systemic risk.
Right. Rust's safety guarantees stop dead at the FFI boundary. The second you call into that C wrapper and into the C++ code, all bets are off.
So your safe Rust code can be corrupted by a memory error happening on the C++ side.
Exactly. Undefined behavior, a data race, anything. It can poison the data that Rust is relying on, completely undermining the whole point of using Rust in the first place.
So you have to treat that boundary like a high-risk perimeter.
You have to. And the smart strategy is to phase your adoption. Start with peripheral things. File parsers, configuration tools, command line interfaces, places where the FFI is simple and the risk is low. You prove the value there first before you even think about touching the template-heavy core algorithms.
That makes a lot of sense. Build trust with the low risk wins first. Which brings us to our third point, and this one feels almost contradictory. It's the unsafe paradox. We've been talking about Rust safety, but now the sources are saying you actually need to use the unsafe keyword. The very thing you're trying to avoid.
You do. To get that last bit of performance, to be truly competitive with C++ EC, you cannot afford every single little check that safe Rust imposes.
Like array bounds checking in a really tight loop.
Exactly. In a core placement algorithm that runs for hours, those tiny checks add up. So using unsafe to bypass them isn't a design failure, it's a necessary micro-optimization.
And the data shows this actually matters.
It does. We saw a benchmark where just using unsafe to suppress index checks in some heap operations gave them a 20% performance gain.
20%, that's huge.
Yeah.
That's the difference between being competitive and not.
It is, but you're right, it feels like a paradox. You're manually telling the compiler, trust me, which reintroduces the risk of undefined behavior.
So how is this different from just writing C++ again?
The strategy is completely different. The goal isn't universal safety from the compiler anymore. It's about the localization and encapsulation of risk.
Okay.
The data from successful projects shows that only a tiny fraction of the code, maybe around 6% of the code blocks, actually needs to be unsafe.
6%. But that tiny slice represents 100% of your manual verification work.
Precisely. And that's the philosophical shift. You accept that a few performance-critical kernels have to be manually proven correct, but you've contained that risk to a tiny auditable surface area.
So there's a new kind of workflow for managing that 6%. It's not just, a programmer hoping for the best.
No, it's a very rigorous, formal process. First, you localize. You put all the unsafe logic into tiny, specialized kernel functions. Then you abstract. You wrap those kernels in a 100% safe public API that enforces all the rules.
And then you have to prove it's actually safe.
You do. You write detailed comments explaining why it's sound, and, most importantly, you use specialized tools. The big one is MIRI. It's the Rust interpreter.
And MIRI runs during your tests.
Yes, and it doesn't just check for correct output. It actively hunts for any violation of Rust's memory model, things that might lead to undefined behavior down the line. It's the only way to be confident those unsafe kernels are truly sound.
Okay, so beyond the code itself, the final set of hurdles are about operational constraints. We're talking about people and tools.
Right, the human side of the equation. And the first thing is the talent. The learning curve for C++ veterans is steep. It's really steep.
They have to unlearn a lot of habits.
A ton. They're used to fixing memory bugs late in the cycle. Rust forces you to get the memory model right up front before your code will even compile. Developers talk about spending days just fighting the compiler at first.
And that initial friction, it has to slow down development velocity.
Dramatically, which can be a huge culture shock for an organization that's used to moving really fast.
And the second big operational problem is compilation latency. We know Rust's compiler is doing a lot of work to guarantee safety, but
Yeah.
what's the impact of that on the developer's day?
It's a flow state killer. For a big EDA project, we're talking CI pipeline times of 15 to 45 minutes.
So an engineer makes one small change, and then they have to wait half an hour to see if it even builds.
Exactly. Their concentration is shattered. You can't stay in the zone. It's a major productivity sink, especially for algorithmic work where you need that fast feedback loop.
But this is a solvable problem. It's not inevitable.
It is solvable. Teams have a playbook. It involves smart CI caching and something we call dependency hygiene, just being ruthless about pruning unused features from your dependencies.
And what about the architecture of the code itself?
You have to design for it. You need a wide, shallow dependency graph. You want as many of your libraries, your crates, to be able to compile in parallel as possible. If you have a deep chain where A depends on B, which depends on C, you're just creating a bottleneck for the compiler.
And finally, there's the ecosystem maturity gap. For a field as specialized as EDA, are the libraries even there?
They're getting there, but it's still nascent. Production-ready parsers for specific chip design formats or advanced simulation tools, a lot of that is experimental.
Which means the company adopting Rust has to build a lot of that core infrastructure themselves.
They do. They're taking on a maintenance risk that in the C++ world, they would just buy off the shelf. It pulls your best engineers away from writing the differentiating algorithms and puts them on infrastructure duty.
This has been a really fascinating look at the friction. So to synthesize it all, it seems the value proposition is this. Adopting Rust isn't a quick fix. It's a long-term strategic investment.
It's a calculated cost shift. You're trading the unpredictable, chaotic cost of debugging memory bugs in production, the C++ way, for a predictable upfront cost in cognitive overhead and architectural discipline.
And the sources are clear that this pays off in the long run with much, much higher stability.
Massively higher.
So the phase strategy for success is clear. Start small with peripheral components like I/O, standardize on architectural patterns like the Arena handle system for new code, and critically invest in a small expert team to own that risky FFI boundary and audit all the unsafe code with tools like Miri.
And looking forward, the real game changer would be a stable Rust ABI, something like Shirab, and that would let you dynamically load Rust components into a C++ application without all this FFI wrapper gymnastics. That would be huge.
Yeah. So we'll leave you with a final thought to think about. The most critical trade-off an EDA firm faces when choosing Rust isn't really performance versus safety today. It's velocity versus longevity. You're consciously choosing to accept slower initial development and a steep learning curve in exchange for a software foundation that is built to last, one that eliminates an entire class of catastrophic bugs for the next decade.
So the question for you is this.
What stands out to you as the biggest shift in engineering philosophy required to make that trade-off successful?